Okay, thanks very much, and thanks to the organizers for the invitation and wonderful conference. So before I get to the subject, which is trying to understand the algebraic relations, trying to classify the algebraic relations between solutions of Painleve equations, I'll just say a few moments, really just a few minutes, about where these equations came from. So, um, so the question goes back to Picard, and he asks what differential equations of this particular form, and here f is a rational function with coefficients in the complex numbers, and we're thinking of y as the variable, and t is just we're thinking of it in the function field c of t, and the derivation is d by dt, as usual. Okay, so what's a movable branch point? Well, okay, it's a kind of singularity that solution to an equation like this might have. So the easiest kind of singularity you might have is a pole, something like this, where here this function has a pole at t equals c. And we say it's a movable pole if the value of c can depend on some initial conditions that you put on the equation. So if it can move around based on some initial value problem that you set up relative to this equation. But there's a worse kind of singularity, of course, one where you have to take a branch cut. We're dealing with the complex logarithm here. And again, it's movable if the value of this c that you take there can depend on some initial value data that you might be given. Okay, and so for instance, solutions of linear ODEs have no movable branch points. And it's true that there's a strong classification of the order 1 equations of this form that have this property. I'm not going to elaborate on the kind of transformations I'm considering here, but okay, so the natural question was to try it for higher order equations, and eventually Painleve and others. So Gambier and Fuchs. Well, by the way, this is the father and this is the son. This is why he's lower. Proved that there was 50 families of equations with this property, and of all these families, most of them could be obtained from previously known functions by normal operations, integration, things like that. And I don't want to go too deeply into those operations. Okay. Oh yeah, sorry, this is Painleve right here. Okay. Okay, so here are the Painleve equations, which are these 6 families that couldn't be obtained by previously known operations. And it's the actual structure of the differential equations. I'll try to avoid writing them down too often in this talk or saying too much about it. They're pretty complicated and nonlinear. But there are some things I want to say really quickly, and that's that these Greek letters, alpha, beta, gamma, delta, these are all complex numbers, and we're thinking about them as parameters which might vary. And so really, Painleve 2 is a family of differential equations, one differential equation for each complex number alpha. And the same for the other Painleve families, but with more parameters. And what do I mean about studying algebraic relations, or maybe differential algebraic relations between solutions of Painleve equations? I mean roughly 3 kinds of things. So the first is that we should study different algebraic relations between solutions of Painleve equations in the same family with the same parameter. So roughly this kind of work was done quite a lot recently by Rani Naglu and Anand Pillai. Also some other work by Naglu, and then also some by me. We should also study possible algebraic relations between solutions of Painleve equations in the same family, but with different parameters. And finally, we should also study algebraic relations between Painleve equations from different families with whatever parameters we want, and all the combinations thereof. Okay, and so actually the last part, all the combinations thereof, is the part that we understand the best from the perspective of model theory, and there's still a lot of open problems in the first part. Okay, So before we really get to that, I want to tell you what we can do, and then sort of what the cutting edge is right now for us. So we know that there can, for certain Painleve equations, for special values of the parameters, there can be complicated algebraic relations between solutions of Painleve equations. That's known. But for this talk, we're mostly going to be interested when at least one of the parameters is generic, okay? And by generic, I just mean transcendental over the rational numbers, okay? So, for instance, it's a result of Rani Naglu and Anand Pillai, in a series of nice papers from roughly those years, that P2 of alpha is strongly minimal and geometrically trivial when alpha is transcendental, when alpha is generic. And I'll try to explain what that means in a minute. And by generic for the families which have more parameters, I really mean the tuple is generic, okay? Although we can prove some results when just one of the parameters is generic as well. So let me say roughly what strongly minimal is. Already it's a kind of transcendence statement in a way. So P2 of alpha, okay, this is a general model theoretic term, but it has this incarnation in the setting that we're in. So P2 of alpha is strongly minimal if there are no order 1 differential subvarieties over any differential field extending the one in which we work. So roughly that means that you can work in some big differential field extending C of t, and there's no order 1 equation whose vanishing implies the vanishing of that order 2 equation in that field K, unless you really pin down the value of your solution. So of course, you could always add a solution to P2 of pi, and then you could add the equation x equals P2 of pi, and of course that would imply the Painleve equation holds, but we're not allowing that. We're just talking about order 1 subvarieties. Okay, so in this context, that's what strongly minimal essentially means. Okay. Now, trivial is harder to understand. It's a kind of transcendence statement, and I'm going to explain it more carefully in the coming slides. But what it means, or the slogan you can think of, is that it means that all of the algebraic relations come from algebraic relations between pairs of solutions. Okay, we'll make that precise going forward. Okay, so here's the main force in my view behind this work of Naglu and Pillai. It's to classify the algebraic relations between solutions of Painleve equations, really in this first case, but for all the families, not just for P2. I just wrote an example there. So what they mean by that is a strong transcendence statement, which is, does the following equation hold? The transcendence degree of n many solutions to this fixed Painleve equation, like P2 of pi, for instance, and its first derivatives, there's 2n of those functions. Well, do they have transcendence degree 2n over C of t? That's the question. At least when the complex parameters are generic. And say in the case of P1, okay, there's nothing to say about the parameters because that's a single equation. This is a result of Nishioka from the late 1980s, I guess. So geometric triviality is a weak form of this equation here. And what it says precisely is if that equation fails, then already it fails between a pair of solutions. Okay, so if the equation up there, number 1, is not true, then already for just 2 distinct solutions, we have lower transcendence degree than we might. Okay. All right, so eventually, Naglu and Pillai proved that for all of equations in families P2 through P5, number 1 holds for generic values of the parameters. They proved something a little weaker than this, but a little stronger than geometric triviality for Painleve 6. Okay, I don't want to be precise. Okay, but I want to elaborate a little bit more on geometric triviality, the weak form of this transcendence statement, because we actually know this statement in non-generic cases, many of the equations. So it was a result of Naglu from a later paper, after he worked with Anand, that Painleve 2 is strongly minimal and geometrically trivial whenever alpha is not in 1/2 plus z, and okay, it's not strongly minimal when you're in 1/2 plus z, but it's not too far away. So there's an order 1 subvariety, and it's given by a sort of Riccati type equation for all of those values in 1/2 plus z. And after you remove that locus, you do get a strongly minimal set. So, maybe if you've followed something in model theory, you've heard these words before. The way of saying this model theoretically is that P2 of alpha has Morley degree 2 and Morley rank 1. It's the union of 2 of these strongly minimal sets. One of them is this order 2, the vanishing of this order 2 equation, but take away the order 1 locus, and 1 is the order 1 locus. Okay, so, all right, so here's Painleve, what I call P2. There's no parameter yet because I want to look at the total family of P2. So roughly here, alpha is a complex number, and then this, maybe you don't remember, is the second Painleve equation. So I'm looking at the pairs alpha comma y, where alpha is a complex number and y solves Painleve 2 of alpha. Now, it turns out that there's a group of transformations, affine transformations of the complex numbers, the group generated by just these 3, so it's Z semi-direct product with Z mod 2Z. And there's a commutative diagram, which I'll explain this carefully because it's essential to the talk, so that whenever you take an affine transformation tau in this group, so roughly alpha goes to minus alpha plus an integer, or some transformation like that, we have the following diagram, and we get this bijection. It turns out to be a bijection with that's rational in the unknown, in the y, and has coefficients in C of t. So I'll explain this more carefully in a second. These are called Backlund transformations, and because the coefficients of these transformations, so they're rational functions where you plug in a solution to a Painleve equation, like P2 of alpha, and you get out some other solution to a different Painleve equation. So here's a concrete example. If you take, say, the affine transformation, alpha goes to minus alpha plus 1, that's in that group, and you start with Painleve 2 of pi, okay, here's pi, that sends pi to minus pi plus 1, and here's minus pi plus 1 up here. Well, this induces bijection between these 2 solution sets to these different differential equations in this family, and this bijection is defined by a rational function with coefficients in C of t, so it induces algebraic relations between between functions that solve P2 of pi and functions that solve P2 of minus pi plus 1, okay? So these are called Backlund transformations, and they play an essential role in what I'm going to do. All of the Painleve families have groups of Backlund transformations, but they're more complicated. I don't want to go through them, and so mostly I'll deal with P2, but similar ideas exist for each of them. Okay, you can read what P6 is. So now, if you think about it, my result was that for alpha in 1/2 plus z, we have this Morley degree 2 and Morley rank 1. For all of the other fibers of Painleve 2, we have Morley degree 1 and Morley rank 1. We're strongly minimal. But Painleve 2 has of alpha in 1/2 plus z had Morley degree 2. And it turns out that orbits of these Backlund transformations give exactly the sets on which the Morley degree jumps, in which, if you look at the family of parameters, the Morley degree is different in exactly particular orbits of these Backlund transformations. And tracking these jumps in Morley degree is an essential technique in what we're doing. Okay, and like I said already, these Backlund transformations induce algebraic relations between solutions of Painleve equations in these fixed families. Now, so there are several natural questions, but one of them is a question that was of Bolch, which was mostly answered by Ronnie Naglu a few years ago. And his question, I've stated in a little different language because it's easier this way, is, well, what happens if instead of looking at Painleve equations in a fixed family, what if you look at, say, Painleve 2 with Painleve 4? Could there be any transformations taking a solution here to a solution here? Or more generally, stated more generally, I guess, could there be any algebraic relations between solutions of Painleve equations, which have generic coefficients, from different families? And, well, the answer is no. And Ronnie Neglu was able to prove this for most of the pairs, except for these two pairs. And so then recently I was able to handle the remaining cases, and the way that you handle it is exactly by tracking these jumps in Morley degree and proving something about the generic case. Okay, so because the groups of transformations here and between these two pairs are a little more complicated, I want to concentrate for the rest of the time about an analogous question, but within Painleve 2, because it's sort of easier to write down and understand. So roughly, we've talked about this, the work of Neglu and Pillay. This was the question of Bolch, which at least generically has been answered now. And now I want to talk about this case here, which somehow it seems more natural to consider this case before this case, but it hadn't. I mean, it wasn't. So it's also easier to write down because Painleve 2 is so much easier to deal with hands-on than the other equations. So here's the theorem that I can prove about it. And I'll spend the rest of the time talking about this theorem. So if we take alpha in the complex numbers, a transcendental over Q, and then beta can be an arbitrary complex number, it doesn't matter. Then there are solutions, F of Painleve 2 of alpha, so this is a solution of Painleve 2 of alpha, and G, Painleve 2 of beta, which are algebraically dependent over C of t, if and only if alpha minus beta is an integer, or alpha plus beta is an integer. That just means that they're in the same orbit under that group action. And in fact, it's true that in that case, the algebraic dependency is given by an actual Backlund transformation. Okay, so roughly this says, at least when one parameter is generic, we know that the only algebraic relations between solutions of Painleve equations come from these classically known Backlund transformations. There are no other possible algebraic relations. Okay, so I'll also concentrate on a particular case. It's the most interesting case, at least to me. It's the hardest to prove, and so it's the most interesting, I guess. Or in some sense, the hardest to prove. It's when alpha and beta are transcendental, but they might satisfy some algebraic relation over Q. The other cases can be handled in a similar manner, which involves one less step. You'll probably get a sense of that during the proof. So let's suppose that they satisfy some algebraic relation over Q without loss of generality. We'll assume it's given by this irreducible polynomial, little q, which has coefficients in the rationals. Okay? And so the first step is that you want to prove that if there's an algebraic relation between these solution sets, then there's some rational map which sends one of the solution sets to the other, defined perhaps over a differential field extension of C of t. This step is non-trivial, but it actually follows in a reasonably straightforward way from the general model theory that Pillay and Neglu developed. Well, and me in the case that one of those is in 1/2 plus z, but okay. All right, so the thing is that if that rational function is defined over a differential field extension, it won't be very good for giving algebraic relations over C of t, right? It will mean nothing, maybe. But it turns out that you can use a slightly deeper result from model theory, which is sort of about I guess, say the rigidity of the maps between geometrically trivial sets, can be used to show that the coefficients on this rational map actually are in Q of alpha beta t. Okay, so you yeah, you really have to have geometric triviality here. This is, yeah, I mean, I can't imagine doing the proof without it at this point, because it would be quite hard, I think, to show this kind of descent result if you didn't, well, it would be hard to guess that it's even true, I suppose. Okay. Right. So, okay, suppose that you can do that. Okay, there are some black boxes there, I'll grant you. But now we have some formula, or, well, okay, really a Q of t rational function, which defines our bijection between the solution sets. Now, think about varying alpha and beta. That's what I want to consider, basically. And because these are transcendentals over Q, so I can look at the collection C comma D in C2, affine 2 space over the complex numbers, so that this function gives a bijection between P2 of C and P2 of D. Now, this set is, okay, by basic model theory, a definable set over Q alg, which in the differential world just means constructible, even constructible in the Zariski topology on C2. And so that means that it at least contains a Zariski open subset of this curve, because of course it contains the generic point of that curve. Okay? So, because that's the point alpha beta that we started with, and that's exactly why we need at least one of those parameters in the statement of the theorem to be transcendental. Okay, now this function, it preserves algebraic solutions. It's a rational function with coefficients in C of t, so it will take a function in C of t alg to a function in C of t alg, for instance. Now, there's a strong theorem of Murata classifying precisely when P2 of alpha has algebraic solutions. It's exactly when the parameter is an integer. And so now you begin to notice that something really strong has to be true about your polynomial Q, okay? So for all but finitely many integers C, you have to have that Q of CD equals 0 has only solutions that are integers D, okay? And remember, and vice versa, and remember that Q we assume to be irreducible, little q we assume to be irreducible over the rationals. Okay, so you should think this is a major restriction on Q, and now there are numerous ways to finish the proof. Here's one way. I mean, you can think of more, for sure. But, yeah, so you can use the Hilbert irreducibility theorem, which just says that there are infinitely many integers C, so that the single variable polynomial Q of Cy in here is still irreducible. But how can that be if Q of Cy has an integer solution D? Well, only if it's linear. And by the vice versa condition, you see that it has to be linear in the other variable. Once you know that it's linear, then, okay, there's a little bit more work to do, but you have to, once it's linear, but you can finish that part. That part's not too hard to see that it actually has to be a polynomial like alpha minus beta equals an integer or alpha plus beta equals an integer, essentially. Okay, so that part's not hard. Then there's a little bit more work, but not too much, to see that the dependency has to be given by a Backlund transformation, one of the ones you actually started with. So those steps are pretty easy. Okay, so that's a reasonable sketch of the proof, I think, with a couple of black boxes, I'll grant you. So for these other families, P3, well, not all the other families, right? You notice I only go up to 5. For these other families, P3 through P5, similar results hold. Of course, somehow the orbit of the group of Backlund transformations on the parameter space of P2 is especially simple to deal with. And so the final step of kind of playing with irreducible polynomial intersecting this discrete set is going to be more complicated in the other cases, but okay, you work it out by more elaborate computations of the same kind of nature. Okay, so one point is, why does this kind of thing that I'm doing in the talk only work for generic parameters? Well, let me revise that, when at least one of the parameters is transcendental. Well, it's because what we're doing is understanding how an invariant, either Morley degree or the existence of algebraic solutions or differential subvarieties, we're trying to understand how that varies in families. And then we're looking at a point and we're saying, well, if it has a certain property at this point, then basically by quantifier elimination in DCF, it has the same property in a little neighborhood of that point. And then we wiggle around in that neighborhood and use what we know about the property as the invariant varies in families to prove something, prove this transcendence statement. So but if your parameters are fixed, like P2 of 5 and P2 of e to the pi, or sorry, not e to the pi, sorry, and P2 of 2, or P2 of root 2, then you can't really do much wiggling around because they're fixed over Q. And so this kind of technique won't work. Now, we do have some ideas for handling the non-generic case, the case where the coefficients are not involve no transcendentals, but you need a sort of additional rigidity type result. And I guess this is just a remark for people who are familiar with it, but if it turns out if you could prove that P2 of alpha were complete in the Colchin topology, in the same way that a projective algebraic variety is complete in the Zariski topology, then you would actually be able to prove additional transcendence results because it would give you this additional rigidity to sort of play with. But we haven't been able to prove that yet. And I'll finish my talk here. Thanks very much. How can you, sorry. Yeah, so, I mean, at this point, we're using this, okay, we're using, in an essential way, this property. So, sorry, maybe I should repeat the question. So the question was, at a certain point, I was able to see that the polynomial little q on the slide was actually a linear polynomial in the indeterminates. How can we do that? Well, it's because we know that these Backlund transformations will be preserving C of T alg solutions. And as a consequence of that, we know that when we plug in, it has to be the case that when we plug in an integer here, the only possible solution is an integer here. And we know that this polynomial q is irreducible. And the only polynomial, I mean, and then, you know, just by well, by this argument or numerous others, I would say. Yes. Yeah. Yeah, sorry, the statement, okay, yeah. So, okay, I agree. What I've written on the slide is that it has to be linear in X and linear in Y, but it also, okay, but I mean something a little bit stronger. I'm not being quite precise enough. I mean that the only monomials which can appear are X and Y. Yeah, yeah. So sorry about that. Thanks for the clarification. Thank you.